Hi class, I'm here to talk to you a little bit about locating the epicenter of an earthquake. I'm going to talk about three different components really briefly and sort of put them together for you in the steps, and then you'll finish them later on either in class or on your own. The first is reading the seismogram, what it looks like, and then the second one will be the travel time graph, and finally plotting up the radius to the epicenter. We won't do all of them, but you'll end up doing three, and you'll have to do a little interpretation on your own. So the seismogram you can see here, typically we shorten all this up, but it would be normally a continuous piece of paper. The first wave to arrive, as you know, is always going to be the P wave, and that's here. I've already highlighted it right there. That's the first motion of the P wave. The next wave here is the S wave, and then over here somewhere, would be your surface waves as they come in. There are two components to this. One is the time measured along the x-axis. The other is amplitude. For our purposes right now, you're going to save amplitude in that measurement till later, measuring it with your ruler in centimeters, or in this case probably in millimeters. And you can see we have a scale over here where you measure from the base level down or up to the highest peak to evaluate the amplitude. We're interested in the lag time. That's the difference in time between the P and the S arrival. And in this case, when I count from 0 to this point here, so from the arrival of the P to the arrival of the S, it's 50 seconds. Okay? Now, how does time convert, or is it related to distance? Well, we assume velocity is known. Time is what we measure. That means we can solve for distance. And we do that using an equation, or in this case, we do a graphical solution, okay, where we have a travel time plot. Okay? Distance on the x, time on the y. This line represents the difference in S and P arrival times, which is really a function of wave velocity. We come to the 50, come across and drop down. We see that there's an intersection here at 480 kilometers. We'll put that in this box over here, 480 kilometers. The next step then would be to, sorry, before I get ahead of myself, find each of the seismograms, S and P wave, travel time or lag time, and then come down here, plot each of those up and get a distance to each of them. All that says is that we know the distance, see, to the epicenter of the earthquake at Eureka, California, where we measured it, or where it arrived and was measured on a seismogram, is 480 kilometers. If we flip over to the next page, we have a map. And that map shows us a bunch of cities, and it has a scale. There's a couple ways you can go about this, but the idea is that we need to plot a radius of a circle, which you can already faintly see here using this tool, which is a drafting compass. It has a pencil on one end and like a pointy end on the other, like a needle on the other end. And we're using this to draw circles, perfect circles. Where we have three of those circles, they'll intersect and show us the location of the epicenter. I'm just showing you one for right now. Now we know on our map we have a scale that goes from 0 to 400 kilometers, which is useful, but we also know that the distance we need to measure is 480 kilometers. So there's two ways to go about sorting this out. The first I show you here, I've taken my drafting compass and I've measured, or actually I've taken a ruler, and I've measured the distance from 0 to 400 is 3 centimeters. Okay? I have a distance of 480 kilometers to cover. So I can set up a math problem here, a little cross multiplication problem. So if 400 kilometers is relevant to related to 3.7 centimeters, 480 kilometers is related to some X number of centimeters down here. So we'll do cross multiplication and we end up with 4.4 centimeters as the distance that we want to have from here to here. So this is where I get out my ruler, and I've already kind of done this, but you get out your ruler and you measure from 0 to 4.4 centimeters. Okay, so I have the correct radius that I'm now going to plot. The alternative approach is to invert this proportion here. Normally we're going from map to actual distance. This time we're going from actual to map distance to plot something on a map. Centimeters over kilometers gives me 0.00925 centimeters per kilometer. 480 times 0.00925 centimeters per kilometer should give me 4.44 centimeters. So 2 ways to get to the same solution. Anyway, I've already measured this out as 4.44 centimeters, which is equal to 480 kilometers on this map. I put the pointy end in the city that corresponds to the seismogram that I was using, okay? And I'm just going to trace with the pencil this shape of, or the radius. So somewhere here along this radius lies the earthquake epicenter. It's okay if the radius goes off the page. This doesn't matter. A map isn't designed to keep the radius inside of it. Okay? Now we need 2 more of these plots, and where they intersect, all 3 of them have to intersect. We'll be able to find or locate the position of our epicenter. Very good. All right. So you'll be wrapping this up either in class or at home.